Good morning. We're going to be discussing the week 4 vocabulary where we're getting into energy, and that'll be our first definition. So, what is energy? It's something that's very important in the universe. Almost everything in the universe is either matter or energy, but energy itself can be difficult to describe. It's a property of matter which allows it to do work. Now, in scientific terms, work means you move it. You push a force on it and it moves a distance. That's what work is. So energy is the thing that allows you to do work on an object, to lift it up, to change its position. It's measured in joules. So if we have something that is energy, you're measuring it in joules, Joules. And 1 joule would, if you put a Newton of force onto an object and were able to move it 1 meter, that would be a joule of energy. Now, one of the kinds of energy that we're most familiar with is electricity. Why electricity? Because it's a form of energy that allows us to transport it from one place to another without a great loss. Energy is interesting in that there are different forms of it, and you can change one form of energy into another form of energy, a more useful form. So electricity in and of itself may not be very useful except for bug zappers. I don't know that we use direct electricity much, but by being able to travel through wires, we can get it from a power plant to your house, and then we can transform the electrical energy into heat, motion, light, all the things that make modern living worth having. You're probably familiar with the term energy from things like energy drinks, and that is a form of energy. It's not electricity, it's chemical energy, the chemicals that we take into our body, which then allow us to move our muscles and do work. So now one form of energy is kinetic energy, the energy of motion. Anytime you see something moving, you are seeing kinetic energy. It has a formula. The formula is 1/2 mass times velocity squared. So the faster you go, the more kinetic energy you would have. The bigger an object is. If 2 objects are moving at the same speed, the object with the most mass would have the most kinetic energy. Now, potential energy is different. It's not an energy that you can see, but it is there. This is energy that is stored. Food, for example, has chemical potential energy. There's energy there, but until it's processed, it's not going to be released. There's elastic potential energy, and there's gravitational potential energy, which we'll talk a little bit more of. The important thing is this is energy that is stored and can later be transformed into a different form of energy. One of the things that's most significant is that kinetic energy and potential energy have a relationship. So here we see a bicycle. It's going up a hill. It has a lot of speed, a lot of kinetic energy, but as it gets to the top, it slows down until the kinetic energy has disappeared. But that kinetic energy is what got it to the top of the hill. And at the top of the hill, it has a lot of potential energy. We know, the bicyclist knows that if he starts going down the hill, he's going to pick up a lot of speed. There's a lot of energy there because of his position at the top of the hill. Now look at this roller coaster ride. We see as the roller coaster is moving around that the potential energy and the kinetic energy are going up and down. The kinetic energy increases when the coaster is going fast. The potential energy increases when it goes up something, and that's when the kinetic energy goes down. The interesting thing is, if you were to take the 2 kinds of energy and add them together, no matter where on this roller coaster we do it, we'd have the same total amount of energy. So the potential and the kinetic energy are going up and down, but added together, they would always add up to the same amount. As one goes up, the other goes down. Now, gravitational potential energy, as I said, is the energy from height. It's the energy an object has because of its position above the ground. The formula is gravitational potential energy equals mass times gravity times height. So if we had a ladder, and you lifted a bowling ball up to the top of the ladder, you're putting energy into this bowling ball by raising it up. And now it sits on the top. It's not moving, it's not doing anything. But you would certainly not want to go to sleep with this bowling ball balanced on a ladder above your head, because you know that if it falls, it's going to fall with a tremendous amount of energy and it could kill you. If instead it were an apple, okay, it's just as high off the ground and gravity is just as strong, but it doesn't have the same mass. So it would have far less energy than the bowling ball does. If I take the apple and lifted it to the top of a skyscraper and dropped it, if there were no wind resistance, that apple would pick up a lot of speed and probably cause some harm because the height would be so great at that point. Here we see a young woman holding a ball up a certain height. When she drops it, it loses gravitational potential energy because the height goes down, but the velocity goes up. It's falling at a faster and faster rate. So again, the kinetic energy will make up for the loss of the gravitational potential energy. And it's why you should always be very careful about things that are hanging or look like they might fall, because that energy is there. And when it falls, it can release a tremendous amount. Rock slides and avalanches can be awfully spectacular, and the amount of energy they release is incredible. Elastic potential energy is the energy you get from stretching or bending an elastic object. So, for example, the slingshot, as I stretch out the rubber band, it gets more and more difficult to do that. I'm having to put more and more energy into it until finally, if I let that go, all that energy, all that potential energy stored in the stretched out rubber band goes into the rock and causes the rock to start moving at a very fast speed with kinetic energy. Here's some guys playing a practical joke on their good buddy who foolishly fell asleep in a lawn chair. I suspect alcohol was involved. They find a couple of really large rubber bands, and they put energy into those bands by stretching them out. They put their friend in there, and they start stretching it out further and further. It's getting difficult. They have to push really, really hard. A great deal of energy has gone into that rubber band, which they now allow to let go all at once, and maybe they miscalculate a little bit. Bit more energy there than they anticipated. Let's go to heat. Heat is something everyone knows about, but they don't always understand it. Heat is thermal energy. The energy of heat is thermal energy, and it moves from a hot object to a less hot object. That's a rule. It always goes from the hotter to the less hot. It's measured in joules because as a form of energy, it should be measured in joules. And it's often confused with a related term, temperature. Most people would say heat and temperature are the same thing, but they're actually extremely different. So our next definition will be temperature. And you'll notice temperature is not measured in joules, it's measured in degrees. Temperature is actually looking at the average kinetic energy of an object. How fast are the molecules and atoms in the object moving? The faster they move, the higher the temperature. It's not the same as heat. And one way of looking at this is to look at different objects that have different temperatures and also contain different amounts of heat. And most people would think that the hotter the object, the more heat it has. But that's actually pretty deceptive, which we'll show in this next slide. So here are two beakers. They both contain water. One contains twice as much water as the other. And when we measure the temperature, they are both exactly at 100 degrees. They are boiling. Neither one is hotter than the other. Which one contains more heat? And the answer is the beaker on the right, because it has twice as much water. Now, every atom of water, every molecule of water has a certain amount of heat. And in this case, the amount of heat that each atom has is the same because they are at the same temperature. But the beaker with twice as much water has twice as much heat because it has twice as much atoms. So that kind of makes sense. You can see where that would be the case. But let's look at one that might be a little trickier to understand. Suppose I took you to the ocean, and the ocean was it's around 65 degrees, a little chilly. And you have a hot, steaming hot cup of coffee. And someone asks you, which one has more heat? The obvious answer that people will probably give is the coffee. It's hot. You can't even put your finger in it without getting burned, whereas the ocean is actually pretty cold. But it's actually no contest. The ocean has vastly more heat than the coffee does. It's true that every individual atom in that coffee cup is hotter than any atom in the ocean, but there's hardly any atoms in that coffee cup, not compared to the ocean. It's got trillions and trillions of times more atoms than the coffee cup does. An analogy would be like, suppose someone offered you a cup full of $50 bills, or an entire swimming pool worth of $5 bills? Well, you'd be crazy not to take the swimming pool. It's true that every bill in the swimming pool is worth less than any one bill from the coffee cup, but there's so many more $5 bills in that pool that would be the smart one to take. The ocean contains a great deal of heat, and every night the ocean actually keeps the earth from freezing by releasing its heat into the cooling air, keeping it from getting too cold. And then in the daytime, it absorbs a lot of the heat from the sun, keeping us from getting too warm. Thermal expansion is the fact that when things get hot, they tend to expand. And the reason for this is when atoms are cold, they're not moving very fast. But when they get warm, when they gain energy, remember again, temperature is average kinetic energy. They're moving now. That's kinetic energy. And when they move, they hit each other, and that causes them to bounce away and spread apart. So thermal expansion means that most objects will expand, get bigger as they get warmer. This has a lot of real-world effects. If you look at sidewalks and streets, a lot of times you'll see these cracks and buckling form. People think it's an earthquake. It's actually that in the summertime, the roads, the atoms that make up the roads are expanding, pressing against each other and causing these cracks and things to form. It's something you really want to avoid. And one way of doing that, I mean, look at this railroad track here. That's going to be very difficult for the train to go through. And that's just from the metal expanding and contracting. Bridges, look at the picture on the bottom. Bridges often have this tooth designs, like two combs that fit into each other. And when the road gets warm and expands, they will come together. And then when the road gets cold and contracts, they will pull apart. But because they have the teeth inside each other, when they pull apart, it doesn't make a hole or a crack. You can still drive right over it and not really feel anything. Thermal expansion also explains thermometers. It's a fluid inside the thermometer that is expanding when it gets warm and therefore rises in the thermometer. That's how they work. Absolute zero is an interesting concept. If temperature is the average kinetic energy of an object, what happens if it gets so cold that it stops moving entirely? The atoms just stop moving. Well, that would be the coldest temperature that there could be. You can't get any colder than things not moving at all. So absolute zero is negative 273 degrees Celsius, a temperature so cold that atoms stop moving. Now, this has never been reached and probably never can be reached, because remember the rule that heat always goes from warm to cold. Well, if you get to absolute zero, you are now the coldest thing in the universe, and all the heat in the universe will be trying to get to you, preventing you from getting to negative 273 degrees. Interesting things start happening when molecules get that cold. So it's an interesting concept that scientists have been playing around with, but it will never actually be reached. And lastly, we'll talk about specific heat. Specific heat is how much energy it takes to raise 1 kilogram of a substance 1 degree. If you have a low specific heat, it means that if you start heating it up, it gets hot. If you have a high specific heat, you have to keep adding heat to it until it begins to warm up. And a good example is right here. We have a metal pan and it's full of water. If you put a metal pan on the burner without anything in there and just turn it on and come back in a couple minutes and touch the bottom, you're going to get burned. That metal turns hot very quickly. If you've put water in there, come back in a minute or so and put your finger in the water, it's barely warmed up. Water will absorb a tremendous amount of heat before it gets warm. This is one of the reasons why it's good that our bodies are made up largely of water. We go outside on a hot day and we do not immediately start raising our temperature. The water is stable. And that also helps keep the earth warm and cold for that reason by absorbing the heat when it needs to and releasing it. In the old days, to keep warm at night, they would have hot water bottles. You would fill this rubber container full of boiling water, put a cork in it, and stick that under your mattress. The water contains a great deal of heat, and it would slowly release it over time under the bed. Now we have electric blankets and electrical heating, but still an important concept. So those are some of the terms for this week, and go take the quiz now. And I will talk to you soon. Bye now.